Welcome to day 12 of the 2024 Advent of Code. Today's is another grid problem. This time we have a garden plot where each type of plant is indicated by a letter, and we have a bunch of separated regions. So for example, this here has 5 regions: A, B as a 2x2, C as this lightning bolt shape, D as a single cell, and E as a block of 3. We separate out the blocks, and then we want to fence off each of the regions from each other. And some of the regions can be within other regions, so our regions don't necessarily have to be convex polygons. So this map here contains 5 regions where the X's represent 4 of the regions, and all of the O's combine to form a weirdly shaped 5th region. In order to determine the pricing for this fencing, the price of the fence required for each region is found by multiplying the area by its perimeter, which is a very weird business practice, but I guess it's modern. And we want to determine the total price by summing all of the fence pricing for each region. So they've given us a larger example with a price of 1,930. So we first need to determine where all of the regions are, and we can do that by flood filling. The idea behind a flood fill is basically if we have, like, let's do our original example. In order to flood fill, we would start from one spot, and then we'd look in all directions, find all A's, find all things that have the same character, and then just keep filling like that until we find all of the A's. And once we have nothing left to search for, we're done. And then to search for B, we might do something like this, find both of those. It's basically the same thing as breadth first search, but we're not really searching for anything, so we won't stop until we've exhausted the search space, or quote unquote search space. And so let's do that. So we can define a list of regions, each of which will be a set. And we also need to make sure we don't look for the same thing multiple times, because once we've found a region, we will have identified what region all of those spaces belong to, so we don't want to search again. So we'll maintain a set of scene locations. Then let's, as per standard, get the rows and columns of the grid. And now we can loop through each cell. If we've already seen this cell before, then we can continue. Otherwise, we'll add it to the scene set. And we will also create a new region, which will be a set. So now what we can do is we need to breadth first fill, basically. So we're going to make another queue. So this queue starts out with only R and C. Basically what we're doing is each time we find an object, we add it onto the queue. So let's give these coordinates. So our queue initially begins at just 0, 0. And then when we look and find another A, we'll add it to the queue. And then we'll look for the next item in the queue, etc. And so the queue starts out only containing our starting point, and now we will just look through all neighbors. So note that it's impossible for one of the neighbors to already be seen, because if we already saw the neighbor in a previous iteration, then we would have already seen our current space in that same iteration. So let's go through the entire queue. So while queue just keeps looping as long as the queue is not empty, we can get the current row and current column using queue.popleft. Now we iterate through all neighboring rows and columns. We need to check a few conditions. So if the neighbor is out of bounds, then we skip it. if the character, if the crop being grown at that cell is not the same as what we're currently at, which we can, at the beginning here, we can say like crop equals grid RC. So if the crop being grown at this place isn't the same as our current search, then we don't want to go there. And otherwise, if it's already in the region, then we don't want to add it again. So if it's in the region, we skip it. Otherwise, we can add it to the region here and also add it to the queue. Once we get to the end, we just need to include all of the crops from this region into this set. We can do that by either doing one add here, or we can at the end do scene pipe equals region. What this does is it effectively does scene pipe region, and the pipe operator takes the union of two sets. I'm not actually sure which one is faster, but I suspect it would be this one because it knows in advance that it's going to be expanding the set by a semi-decent amount, but don't quote me on that. I am not exactly sure how Python sets work. And then once we have that, we can just add this region to the list of regions. And let's just double check our work. This should give us all of our regions as a list of sets. Now that we have the regions, we need to get the area and the perimeter. The area is trivial because it is just the length of the set. The perimeter is less trivial. So let's make a function that gets the perimeter of a region. Suppose we have a region that looks like this. In order to get the perimeter of this object, we can consider breaking it down into its constituent squares. Each square has a perimeter of 4 on its own, and so if we just multiply the number of squares by 4, we get an initial number, nowhere close to being the actual perimeter, but just a number. Then we note that for each pair of neighboring squares, their two edges will be eliminated as they are facing each other and do not count as part of the perimeter. Essentially what that means is for each square, we look at all 4 sides, we identify where there are neighboring cells that are in the section, and if for each one that exists, we subtract 1 from the initial perimeter guess of 4. This does mean that a region consisting of a single cell would have a perimeter of 4. A square next to another square has a perimeter of 3, which makes sense. A square that is in the middle of a line only has a perimeter of 2. A square that is part of a T-block only has a perimeter of 1. And a square that's completely contained within a region has a perimeter of 0. So we can define the output as 0 initially, and then we can go through each item in the region. So for our C in region, we can increase the output by 4, and then for each neighboring potential neighboring coordinate for NR and C in these, if NR and C is in the region, then we decrease the perimeter by 1 again. Now we just need to take the sum over each region of the area times the perimeter. And so that gives us our answer for part 1. Or almost. Oh yes, I did not add the starting point to the region. The starting point of the flood fill obviously needs to be part of the region itself. With that fixed, that gives us our answer for part 1. I'd like to take a moment to introduce my sponsor, CodeCrafters. Many people ask me how I learned to code, and I've always learned best by actually going in hands-on with a project or problem rather than reading documentation or tutorials. That's why I love CodeCrafters, a platform that lets you build real-world software to both develop your problem-solving skills and train you in a specific language of your choosing. CodeCrafters lets you choose something to build, such as a BitTorrent or Git clone, and a language from a growing selection of over 20 languages and counting. You simply clone a repository from them, write your code to build your project with their intuitive step-by-step process, and push to get immediate feedback. I've been meaning to learn Rust for a long time, and when I get the time, CodeCrafters will be my choice for how I go from no experience to someone ready to start building my own things in Rust. Whether you're a beginner or already experienced in a language, CodeCrafters is a great way to start coding, pick up a new language, or master your language with its selection of projects. Doing a project teaches you more than just coding, as you can learn about protocols and existing software such as TCP, Kafka protocols, the inner workings of SQL databases, and more. If you sign up for free via my link in the description, you'll get 40% off if you choose to upgrade, which unlocks more content, gives you priority on test runs, grants access to perks which can save you money on all sorts of other platforms, and more. Plus, if you sign up within this December, you'll get access to all of the problems for free for 1 week. If you work at a company with learning and development benefits, be sure to check if CodeCrafters would qualify, so you don't even need to pay for it yourself. Thank you for your support, and let's get on with the rest of the video. Moving on to part 2, it looks like we are eligible for a bulk discount here, and instead of using the perimeter to calculate the price, we use the number of sides. And so the price of the fencing for each region now goes from being the area times the perimeter to the area times the number of sides of the polygon it represents. And it includes a note to be careful when counting the fence around regions like this one, where we see that there is like a corner point here. It notes that fences have insides and outsides, and so the fences do not connect across the middle in this area here. So to visualize that a bit better, let's suppose we have a garden that looks something like this, where the middle region is not part of the garden. Then this is not one edge. So let's work backwards here. I have two solutions here. The first one I'm presenting is going to be the one that I came up with during the contest, and the second one is one that I have not tried whatsoever, so you will get to experience the debugging process together with me. So looking at the edges, we can see that this one has 12 edges. In order to determine this, we need to note that because this does not count as one edge, then it follows that we need to track which direction each side is facing. So if we mark the side that is not part of the garden with red, then this is what we have now. And so these are the individual sides. We see that we drew 12. And now if we are to separate these into individual squares again, like they were previously, then we can see that we basically have a bunch of individual edges, each edge having a direction. So how could we determine where all of the edges are? Because these interior edges do not count. So we can use a sort of half Cartesian coordinate system. So if we imagine a coordinate system, which we already conveniently have because we're operating on a grid, let's suppose that these cells have the following coordinates: 1, 1, 2, 1, 2, 2, and 1, 2. It stands then to reason that realistically we could indicate the coordinates of an edge based on the two squares that it sits between. And so we can give this a coordinate of 1, 1.5. Basically, we take the average of the two squares that it touches. This one can have a coordinate of 1.5, 2, and we can see that intuitively this makes a lot of sense. 1.52 means that it sits at y equals 2, which means it sits along this slice where the blocks sit, and 1.5 means that it's to the right of the 1 column where these sit, but also to the left of the 2 column where these sit, meaning it's the edge between the two. Continuing that logic, this edge becomes 2, 1.5, and this edge becomes 1.5, 1. Now, under this system, we could also represent corners by just looking at all 4 of the squares they touch and averaging them all out, which gives us 1.5, 1.5, but that is not currently relevant. So let's get rid of our perimeter function and let's look for the side count given a region. So in order to determine the number of sides, we're first going to need to get all of the edges. To get all of the edges, what we're going to do is we're going to look at each square and look at all 4 of its edges again, just like with perimeters. But what we're going to do is, if we, instead of adding 1 to the perimeter count, if we see that the neighbor 1 exists, we're not going to add the edge. Otherwise, we are going to add the edge, making note of which direction it's facing. For consistency, I will mark the facing of an edge as the direction from the edge towards the center, or towards the square. What that means is this edge, if we consider this edge here where this square is where the edge originates, then it would have a facing value of negative 0.50. What this tells us is that it is facing leftward in its row, and it is not facing anywhere in its, or sorry, it's facing leftward in its row and nowhere in its column. Basically, because this edge here had a coordinate of 1.52 and this square here had a coordinate of 1, 2, we just subtract the square coordinate from the edge coordinate, which gives us this half coordinate, which will be one of plus or minus 0.50 or 0 plus or minus 0.5. And so once we have all of those edges, we can proceed from there, but let's get all of those edges first. So we're going to have a set of edges, and now we can go through each square. So for RC in region, we will look at all of the neighbors to determine if we should be adding that edge. So for NC in, it would be really nice to have a utility for this. So for each of the neighbors, if the neighbor is in the region, that means that this is not an edge because both sides of the edge are inside the region, so we skip this. Otherwise, in order to get the edge coordinates, we can take the average of the 2 squares. So this is the origin square and this is the outside square, so the edge sits between them, and we can take ER as R plus NR divided by 2, EC equals C plus NC divided by 2. So this now gives us the average of the 2 square coordinates, which, as we know, is an edge coordinate. We're going to make edges actually a map from each edge to the direction it's facing. So then we can do edges EREC equals its facing direction, which will be the edge minus the origin square. So ER minus R and EC minus C. So now we have all of our edges, and if we check our work, we can, let's just try this for a second. For region in regions, print sides region. And just to make sure we can identify which region it is, we can also just grab the, we can do this. Print RC equals list region 0, print grid RC. And if we run this on our test code, we can see that the M region here has a couple of edges. So let's look through these. 9.50 means that it's in row 9.5, meaning it's between row 9 and row 10. In this case, row 9 is the last one, so that would be the bottom edge, and it's in the 0th column. So that would be the bottom edge of this M here, the bottom left one. And its facing direction here, sorry, I'm looking at the wrong output. Anyway, its facing direction here tells us that it is facing up in row, or sorry, it is facing up and it is not a side edge. This here tells us that it's exactly in row 9, so it's one of the edges in this row, and it's at column negative 0.5, meaning it's to the left of column 0. So it's the left edge of the bottom left M, and its facing direction tells us that it's facing right, I suppose. I think that makes sense. Yeah, because a positive number means it's facing up or left, and negative number means it's facing right or down. Because it's kind of inverted. We're looking from the edge towards the square rather than vice versa. So now that we have all of our edges, we need to piece them together into sides. In order to determine if two edges should be in one side, we check if they are next to each other and facing the same direction. So for example, in our above case, because these two edges are adjacent but not facing the same direction, they do not get pieced together. We can again run a flood fill, where essentially we select an edge from the list of edges, and then we go through in both directions until we hit the end of it and strip out all of those from the set. So what we can do is we can loop through each of the edges. So we can say for edge in edges.keys. I guess we can do for edge direction in edges.keys, and we can also maintain a set of scene edges. So if edge in scene, then we skip, otherwise scene.add edge. And we also need to maintain a count of edges. So side count equals 0. Each time we find a new edge that hasn't yet been seen, we increase the side count by 1. And then we can go in both directions and look for adjacent edges that are facing the same direction. So we can get edge row, edge column out of the edge. If the edge row is an integer, then that means that this is a side edge. And so we want to go up and down, which means that we want to increase or decrease the row. So in order to do that, we can get the current row, which, we can get let's shorten these variable names a bit. So ER means the edges row. So we can do CR. So we can say CR equals, we need to go up and we also need to go down. Let's pack that into a loop. So for difference in row in -1, 1, we can set CR to be the next space over. So that would be the current row plus DR. And then while CR EC in edges, what this means is we're taking the current row and the edges column, because the column never changes, and we're checking if that is one of the edges. So if that is an edge, and we also need to make sure the direction is correct, and edges CREC equals direction, basically that says while the next edge over is indeed an edge and does actually face the same direction, then we will we'll add it to the scene set. We can simplify this a bit by doing next edge equals CREC, and instead of checking if it's in the dictionary and then getting its value, which requires 2 lookups, we can just do edges.get CREC, or next edge rather. This will return none, which is Python's equivalent of null, if the key is absent. And so that automatically gives us a fail on the direction check. So basically this has 3 possibilities: same direction, opposite direction, or null. If we get a null, it means the next edge over doesn't exist, and so we want to stop anyway. And then we can add next edge to the scene set, marking it as already seen, so that when we get to it later on, we do not count it again. And then this will go first up and then down. If our edge row is not an integer, that means our edge column is an integer, meaning that this is a horizontal edge, so we want to go left and right. Therefore, we want to change the column. We'll basically copy this over. where instead of changing the row and keeping the column, we keep the row and change the column. And then this part is actually just identical. There's probably a much cleaner way of writing this, but I leave that as an exercise to the reader. Finally, we can return the side count to give us... right, I forgot to remove the debug code. This will hopefully give us the answer. Just to flag what I was doing wrong here, .keys gets the map keys of the edges, which would be the actual list of edges. I was originally not doing this part, so this would have been correct, where edge would be a pair. But because this is returning pairs, and this was trying to unpack them, which means that edge ended up being the row coordinate and direction ended up being the column coordinate. .items returns a dict items object, which is basically a list of pairs where each pair has the key and the value for each entry. It's the equivalent of .entries in a lot of languages. And we also are running into an infinite loop issue, which is probably, it's being caused by me not advancing the while loop. Yeah, so we also need to actually advance the while loop. So never mind, this thing won't work. After our loop iteration, we also need to step forward once more. We can't just stay in the same spot as last time. And correcting those issues, that now gives us our answer for part 2. Now I wanted to show off a second way of doing this, which I am not sure will work yet, but we can explore this together. So instead of looking at the side lengths, or the number of sides, we can look at the number of corners, because in any polygon, they're going to be the same. And that seems a bit easier because we don't need to try to piece together the edges. Basically, for each corner coordinate, we have a couple of possibilities. If it only has one side, that means that it is one corner. If it has two sides that are adjacent to each other, then it's not a corner. If it has three sides that are adjacent to it, then it is one corner. And if it has four sides adjacent to it, then it's not a corner. And finally, if it has two sides but they're not adjacent, then this actually represents two corners, because again, remember that this polygon here and this polygon here do not have their edges cross over, which means that if we did like this, for example, like in the last example, then we would need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this would need to be both the 11th and the 12th corner. Looking at the corner positions is going to be a bit more difficult, but should still be relatively straightforward if I am not underestimating the difficulty here. Basically, what we're going to do is, in order to identify all of the corner candidates, we're going to just take a look at every single cell in the region and identify its four corners. Again, remember that we're using half coordinates, so basically these are displacements of plus or minus 0.5, plus or minus 0.5. So that represents our four corners. So corner candidates equals set for RC in region, corner candidates dot add, we can say like for CRCC, which, sorry for the confusing variable naming, but instead of current row and column, this now means corner row and column in RC minus 0.5, or sorry, R minus 0.5C, R plus 0.5C, RC minus 0.5, RC plus 0.5, corner candidates dot add CRCC. And now we just look at each corner and look at how it is configured. So for CRCC in corner candidates, and we ultimately need to get the number of corners here, we look at its 4 surrounding squares and figure out which ones are occupied. So we can do that by saying config equals square row square column, or square row square column in region for srsc in, and then we can basically just take this, except these are edges, not corners. There we go. This actually does the correct thing. We can basically just take this again and just copy paste it over here. It's interesting because this exact list goes from a square to its surrounding corners, but also goes from a corner to its surrounding squares. And so what this is basically doing is it's looking at the 4 squares around it, and it's checking which ones are in the region. So if we print the config, then let's see what happens here. This is going to give out a bunch of errors, but we can see that we get a bunch of length 4 lists. This is the square above it to the left, below it to the left, above it to the right, and below it to the right. It's probably a bit easier if we visualize going in a circle, so let me just adjust these signs for you. Okay, so now what we're doing is, given a corner, we are looking at the cell above it and to its left, and then below it to its left, and then below it to its right, and then above it to its right. So we're going around in a circle. So the number of squares is equal to the sum of the config. Now, config is a list of booleans, but in Python, true is the same as 1 and false is the same as 0. You can see here that you can treat them exactly as numbers and it'll work just fine. And so if we take the sum of a list of true and false values, we just get the count. We have a couple of cases. If number is equal to 1, then that means that we have a case like this, which represents 1 corner. If it's equal to 2, then we need to check if they are adjacent, which means no corner, or if they are opposing, in which case we have 2 corners. In order to do that, we can say if config equals true, false, or config equals false, true, because basically what we're saying is, in order for the corners to be opposing, we only have 2 possible outcomes. Either they're in the top left, bottom right, or they're in the bottom left, top right, which represents a true in slot 1 and 3, or a true in slot 2 and 4. So these are the only 2 possibilities. In all of the other 4 cases, we have no corners. So corners plus equals 2, otherwise corners plus equals 0, so we can just exclude this case. If the number equals 3, we also have 1 corner. And the final 2 possibilities are a number equals 4, in which case we don't have a corner at all, or numbers equals 0, but that's impossible because all of our corner candidates were derived by looking at corner positions next to squares, so at least its originating square must be in the config. Theoretically speaking, this should give us our answer, and we see that it indeed does. I was not entirely sure this would work so well, but it looks like this solution does end up being a lot more straightforward than actually counting the sides. So yeah, neat trick. If you're asked to count the sides, consider counting the corners instead. Just be careful with your double counting of corners. In any case, I hope you enjoyed this video, and I hope you learned something. Thank you for watching, and I'll see you next time.